Hey everybody, it's been a while since I did a video and I might have forgotten how to do it, but we're going to give it a go anyway. Today we're doing probability, which is a bit of a funny topic because some people, i.e. the foundation students, will find this fairly straightforward, I think. To my mind, is one of the easier topics there is to understand. However, higher tier students, I think it's also one of the toughest. An awful lot of the A star questions coming born out of the topic of probability, and as such can get a little bit tricky, especially when we start putting tables etc. into it. So what I'll do, I'll start off and I'll do the foundation tier stuff up to a certain point, and then we'll cut and we'll put the higher tier stuff in, so you can only need to watch as much as you need to, um, which maybe saves a bit of your time. And then when we get into class next week, we'll be able to let's do some experiments. Let's have a bit of fun with it, and then get a bit of the competition going, because I know you're all very competitive people. I'm gonna give it a rattle. So, probability. Today's objectives. There's three that I'm gonna go for, and they'll look a bit funny. Well, two of them do it anyway. We're gonna understand the following three things. We're gonna understand what this not less than or equal to p of x less than or equal to 1 means. We're gonna understand what oh god, the Greek letters, the pain. Sigma p of x equals 1. And then something that maybe makes a bit more sense. The probability is equal to the number of favourable outcomes over the total possible outcomes. And they're the three things we're going to understand. The first two look scary, but they actually mean something fairly straightforward. I only put them in there to be a bit obtuse about what we're going to learn. So, first thing I'm going to do, I'm going to consider each of the following statements, right? So I'm going to put 4 statements in front of you, and I'm going to get you to declare how you would best define the probability that each will happen using one of the following words. So the words we're going to use are unlikely, impossible, likely, certain, and even chance. So using one of those 5 words, how would you best describe the chances that you would watch TV when you go home tonight? Now you can pause, or you can answer, you can write down what you think. A lot of people will say certain. They'll say, well, Chris, I watch TV every night. Without fail, you know, see what your man's doing on EastEnders. I can't believe he's doing that to her. It's absolutely unbelievable. I just can't stop watching it. It's just ridiculous. Kind of comes to my mind that actually aren't soaps a little bait out, as the Belfast phrase would go. You know, kind of regurgitating storylines again and again, but different characters. Back on topic, I would ask you the question, or would challenge you in saying this. What if you got home tonight and there was a power cut? What if you got home tonight and there was a family emergency? So you get home, the cars were all parked outside, and something had happened. Somebody was ill, touch wood, doesn't happen, etc. What would you do? Now, a common answer I get to this is that some people go, well, I'll go to my granny's and watch TV. If my power's out, what if her power's out? You're going to drive to Newry, being the closest place with power, or something like that, just to watch EastEnders. Do you even know anybody in Newry? And the family emergency one, well, the common response I get, well, do you know what it is, Chris? See, if I get home and something's happened to somebody, I'm just going to say to my ma, whoa, hold on there. I have to go in here and watch TV for even 30 seconds because I have to prove Chris wrong. He thinks he's a smart guy, and I'm going to prove him wrong, that I am going to watch TV tonight. So there. And while this all may be true, it isn't one of the things that we would consider certain to happen. There are things that could get in the way of you watching TV tonight. When we come to ones later on, you'll see things that are certain, but that wouldn't be one of them. It might be highly likely, and again, we'll look at this in a second about it. When you say highly likely, what does that mean with regards to certain? But it's not certain. There are things that could happen to stop that from happening. What about the next one? The chances it'll get dark tonight. And I should qualify this by saying in Lisbon or Northern Ireland. Well, this is certain, because it's got dark every night, and there are good scientific reasons why it gets dark every night, and it's going to get dark tonight. It's just one of those things that is certainly going to happen. If you lived in the Antarctic, yeah, I think it's the Antarctic rather than Alaska, they get no darkness for a good portion of the year. So in that case, there would be a chance, etc. But where we are, it gets dark every night, so that one would be certain. Chances that you'll meet a dinosaur on the way home today. Right, for most of you, that's going to mean impossible, because you're going to say that dinosaurs were extinct or are extinct and have lived here for a long time, so chances of meeting a dinosaur on the way home are none. However, some people might walk past a dude in a Barney costume every couple of days, and they might interpret that question slightly differently. So, a bit like when we were talking about our questioning, you have to be careful about what the question is asking you, and make sure you've framed your question properly. That dude in that Barney costume could high five you on the way past, and you go, "Well, there you go. It's not impossible. Bit freaky looking, but not impossible." Last one. The chances you'll win the next time you buy a scratch card. Some people will say this is an even chance, but think of it this way. One, do you think the lottery company would make any money if an even chance or you were even likely to win a scratch card next time you bought it? Or think of it like this. Do you think there are more losing scratch cards than there are winning scratch cards in the pile? Well, there are more losing scratch cards than there are winning ones. So in that case, that proves that it's going to be unlikely. The chances are that you're going to get one of those non-winning scratch cards rather than the others. Excuse my yawning. It's only the afternoon. Okay, let's do an experiment. We're going to consider rolling the dice. If I asked you what were the chances of rolling a 6, and I told you that the way we define probability is this. Probability is a fraction, and where the top number is the ways in which a statement can be true, divided by the total number of possibilities. So if we use the example of rolling a 6, what's the chance of rolling a 6? The ways in which that statement can be true can only be one way. The only way we can roll a 6 using one day is to actually roll a 6. If we roll a 4, that's not a 6. Roll a 3, that's not a 6. The total number of possibilities when rolling a die are 6. There are 6 sides, or 6 faces to a die, so there's 6 possibilities. So the probability of rolling a die 6 on a dice is 1 out of 6. What if we say an even number? Well, there are 3 even numbers on a die, single die, a 2, a 4, or 6. So there are 3 ways in which that statement can be true, that it can get an even number, but there are still 6 possibilities, so the probability would be 3 out of 6. Here comes the semantic argument. Do you simplify down the 3 over 6? Or do you leave it as 3 over 6? So if I simplify 3 over 6 down, you'll get a half. I suggest not. And the reasons I use are this. If I get a probability, sometimes I can guess what the question was about, infer just by giving the probability. For instance, if somebody tells me the answer to a probability question is 13 over 52, there's a fairly good chance that the question was, what are the chances of picking a heart, a club, a diamond, or a spade from a deck of cards? Because 52 is the number of cards in a deck. The chances are pretty good that if 52 is the bottom number, then it's going to be it's going to be about cards. If I simplify that down, I get a quarter, and a quarter could be the answer to anything at all. So in probability, I suggest that you don't simplify it down unless it says simplify your answer down to the simplest form in a fraction. Let's do another couple. What if I ask you for the probability that we'll roll a number less than 7? Well, the ways in which it can happen 6 ways. You can roll a 1, 2, a 3, a 4, a 5, or a 6. And that would be 6 out of 6. Now, if you do 6 divided by 6, or how many 6s in 6, you'll get the answer 1. And I'll ask you to think about what if I asked you to describe that in words like we did beforehand. What if I ask you for the probability that we can roll a number less than 7? What word would you use to describe it? Well, you would say certain. Every time you roll a 6 out of die, or a normal die, you're going to get a number less than 7. You say certain. So what we can say is that certain is equal to the value 1. Similarly, what if I ask you for the probability that we roll a number more than 7? Well, the survey says in this case, you can't roll a number greater than 7 using a 6-sided die. It's impossible. If we define it as impossible, but work out the probability, it's not out of 6. And not divided by 6, or how many 6s are not, is not. So we'll find out that impossible is equal to the value not. And what we get is a probability scale. Right? So probability is a measure of how likely or unlikely an event is to occur. So probabilities are usually written as fractions like we've been doing, but you could write them as decimals and percentages because you can easily switch between those, as we've discovered beforehand. So 3/4 could be 0.75 or 75%. It's all well and good. So probabilities can lie anywhere between 0, the impossible, and 1 certain, and what we get is a scale like this. We have impossible at this end, certain at the other end, and they will have these values. Impossible is not, certain is 1, and even chance, 50-50 chance, or a half is in the middle. And what you find is the more likely something is to happen, the closer that fraction or decimal percentage will be to certain. The less likely that it is to happen, the closer it will be to impossible. So, an event with a probability of 0.8. So if I put 0.8 on the scale, it would appear somewhere up there. And we would describe that as very likely, because it's more likely than just likely. It's kind of the right hand side of that line, if you can say. What about a probability of 0.4? Well, it's going to be close to even chance, but still in the unlikely side, so it's say unlikely. Third one, probability of 1 over 20. That's going to be nearly impossible, or very unlikely. It's going to be right down the bottom down there. An event with a probability of 6 over 12. Well, 6 over 12 simplifies down to half. You're going to say that's even chance there. And that's how we use the probability scale to define probabilities using words from figures. Next. So that's to complete the probability scale using the words given just from before. So your even chance goes in the middle. Your likely goes to the right of that. Possible, certain, unlikely is there. Okay. And we've got to label the events given below on the probability scale. So the chances of getting an even number when rolling a die. Well, it's 1 out of 6, isn't it? Sorry, getting an even number, sorry, is 3 out of 6. So you can roll a 2, 4, or 6. So it'll be 50-50. Chances of winning the lottery are nearly impossible down there. And the chances of rain in March are quite likely, because we live in Northern Ireland and it rains an awful lot. If you want, you can describe an event you think is a probability of about 0.3. Or something that's a probability of 1, i.e. certain, or probability of 0.8. But we're going to move on and do some examples. So Paul was picking from a bag containing tiles numbered 1 to 10. There are 10 tiles inside. And that's the only thing that's inside the bag. Write down the probability that the number he picks is a 7. Well, how many tiles will have the number 7 inside? There will only be 1. So that probability will be 1 out of 10. What about the probability of picking a tile that's 4 or less? Well, that will include the number, the tile that says 4, 3, 2, or 1. So there are 4 tiles there, so the probability would be 4 over 10, which you could simplify down to 2 over 5 if you really want to. An odd tile, well, what odd numbers are there in 1 to 10? There's 1, 3, 5, 7, 9. There's 5 of them. 5 out of 10, or a half. A multiple of 3. Many multiples of 3? 3, 6, 9. There's 3 of them, so 3 out of 10. And that would be the answer to those questions. A survey is conducted of pupils' favourite team. We've got Spurs, Manchester United, Liverpool, and Arsenal. No Everton. Survey is wrong. John picks the people at random and asks more questions. Write down the probability that the team that he supports, Liverpool. So the first thing you're going to have to do is work out your total number of possibilities. We can see how many people support Spurs, see how many people support United, Liverpool, and Arsenal. We need to work out how many there is altogether. In order to do that, we'll just add these all up. 12 plus 8 is 20. 20 plus 4 is 24. 24 plus 6 is 30. And we'll get that there are 30 people. So the probability of somebody supporting Liverpool is the number 4, because 4 people support Liverpool, over the 30, which is simplified down to 2 over 15. A London team. You need to know something about football and geography. The 2 London teams are Spurs and Arsenal. So there are 12 plus 6, 18, still out of 30 altogether. So 18 over 30, which goes down to 3 over 5. And not Liverpool. Well, if there are 4 over 30 that support Liverpool, then there are the other 26 out of 30 that are going to support not Liverpool, which is 13 over 15. Third one. A package here, 20 coloured balls, some red and some blue. Keith knows that the probability of picking a red ball is 2 out of 5. How many red balls are there? Well, you're just going to use your fractions then. So 2/5 of 20. 20 divided by 5 is 4. And 2 multiplied by 4 is 8. So there are 8 red balls. How else can we use this? So here's a table which shows information about the number of goals scored by Aston Villa in each game so far. Mr. Walker has all the games on TV and decides to watch one. He picks a game randomly. What is the probability he picks a game with exactly 1 goal by Aston Villa? Well, again, we've got the same problem. We need to work out how many games there are, total number of possibilities. So there were 3 games with no goals, 6 with 1, 5 with 2, 4 with 3, 2 with more than 3, etc. If I add those all together, I get that there's a total of 20 games. 3 plus 6 plus 5 plus 4 plus 2 gives me 20. So the probability of exactly 1 goal by Villa is 6 over 20, which is 3 over 10. 2 or more goals by Villa? Well, they could do that by scoring 2, 3 or more than 3. So that'd be 5 plus 4 plus 2, which is 11, and again out of 20. Last one, since we've just done cumulative frequency graphs or curves. The cumulative frequency curve below shows the distribution of the height of 50 students. Estimate the probability the student picked at random will be more than 164 centimeters tall. So you would go to your graph, find 164, draw your line up, draw it across. It'll look a bit like that, and we'll get to 40. What's the probability that a student picked at random will be more than 164 centimeters tall? Well, that's going to be, there's 10 students with more that are higher than that. So it'll be 10 out of the 50 students altogether, or 1/5. And that's some questions. Okay. So that's where the bit that the 0 less than or equal to x less than or equal to 1 comes into. That just says that all probability is measured between 0 and 1. Total probability of events. And this is where we use this Greek letter called sigma. We used to call it sum of p to the x1 equals 1, where an experiment there must be a result. So we're going to roll a dice, for instance. You'll always get a number between 1 and 6. There's an outcome every single time there. So that's an example of a situation where something must occur. So what this means is that the sum of all probabilities add up to equal 1. So if I use the example that the probability of rain is 0.7, right? If the probability of rain is 0.7, the only other thing that can happen, or the opposite of that, is that it's not the rain. And if they add up to 1, you would get 1 minus 0.7, which is 0.3. Similarly, a coin is based, so the probability of heads is 3 over 5. The only thing you can have is a tails. It'd be 1 minus 3 over 5, which is 2 over 5. We've got a 4-sided spinner, and has the following probabilities of each number. The probability that the spinner will land on a 2 is equal to the probability that it will land on 4. Complete the table. Well, for those algebra geniuses amongst you, you could just call that number x, or that fine notate it as x, because 2 and 4 are the same. So we know that all those things added together are going to equal 1. So you'd have 0.2 plus 0.3 plus x equals 1. That's not 2x plus 0.5 equals 1. If you solve that down, you'll get 2x equals 0.5. So 1x is going to equal 0.25. And that's how you'd solve that one. Let's see. A die is based so that the probability of rolling a 6 is 1 over 4. What's the probability of not rolling a 6? So it's everything else apart from 6. So it's going to be 1 minus a quarter, which is 3/4. A die is based so that the probability of each number is this. It's exactly the same as the previous example, except we've got 6 numbers now instead of a 4-sided spinner. So we'd add all those bits together: 0.1, 0.15 plus x plus 0.2 plus x plus 0.05. But that would give us 0.5 plus 2x equals 1, and again x would equal 0.25. And the last one, the weatherman claims that it's twice as likely to snow as not. Complete the table. This one's tricky because it's using ratio. And if something's twice as likely to happen as not, that means for every 2 out of 3 times that it snows, that's going to be the probability. So it's going to not snow 1 out of the 3 times. So not be out of 2, it'll be out of 3. And that is the total probability of events. Let's consider this. We're going to play a little game. So each horse moves one square if you get its total when you roll 2 dice. Is it a fair race? It's not a fair race. Why isn't it fair? Well, consider the possible outcomes from finding the total of 2 dice. And what I'm going to do is I'm going to use a table for this. So we're going to write down what you would get if you roll a 1 and a 1. And if you roll a 1 and 1, you get a 2. If you roll a 1 to 2, you get 3. 1 to 3, you get 4. 1 to 4, you get 5, etc., etc. Similarly, 2 and a 1 would look like that, and your table will be filled out as such. Now, we know the probability is the number of desired outcomes over the number of possible outcomes. So the total number of different outcomes that we can have is all these bits in here. There are 36 squares in total. So our probability is out of 36. So if I asked you, what's the probability of rolling a 2? Well, there's only 1 2 there, and it's right there. So the probability of that is 1 out of 36. What's the probability of rolling a 3? Well, there are 3s there. There's 2 3s. So the probability is 2 out of 36. What about 4? It's 3 out of 46, and etc. etc. So, which horse is most likely to win? Well, it's going to be horse number 7, because it has the highest probability. There's 6 chances out of 36 when you roll the dice that you'll get a 7. Because you can do 6 and 1, you can get 5 and 2, you can do 4 and a 3, 3 and a 4, 2 and a 5, and a 6 and a 1. The least likely horses to win are 2 and 12, because they've got a probability of 1 out of 36 each time. Okay, and similarly, if we do the same thing, except this time we would multiply the scores together, you can fill out the table as below. You can pause the video and do it. And you should get something like this. Use your completed table to find the probability of getting a score of 12. Well, again, there's 36 total possibilities. What's the probability of getting a 12? Well, there are 1, 2, 3, and 4 different times that the 12 appears. So that probability would be 4 out of 36, which is 1 over 9. Let's use the table to find the probability of getting a score of 23 or more. Well, there's not that many 23s or more in the table. In fact, there are 1, 2, 3, 4, 5, 6. There are 6 outcomes out of the 36 that give a score of 20 over 23. So that's 6 over 36, or a sixth. And I'll not do the next one. You can pause it and do it yourself. There's the answers if you want to do it. Okay. Or that one. Tree diagrams. Right. Sometimes when we were talking about maybe judging the probability of things happening together, we would use things like tree diagrams. And what the tree diagram does is help it make it clear about what you're doing, and see all the possibilities and see the flow of possibilities. And we'll set one up now. Say a coin is passed, so the probability of throwing a heads each time is 2/3. If we look at the first time we throw the dice, or throw the coin, we either get a heads or a tails. So we have 2 possibilities, and we'll start off a tree as such: heads, tails. What would happen is we would label the heads as being 2/3, and if total probabilities have to add up to 1, then the probability of a tails must be what? Must be a third. Okay. What about if we threw the thing for a second time? Well, we'd have a probability of a heads or tails for each of those things as well, and we'd label it the same: 2/3 and a third, 2/3 and a third, 2/3 and a third. The branches show their possible outcomes and their probabilities. So, a head or a head is shown there, etc., etc. And any chain of branches from the beginning to the end represents a combination of outcomes. So, the probability of rolling 2 heads would be represented by those 2 branches. Probability of rolling a heads and then a tails is that. A tails and then a heads is that. And a tail and a tail is that. Simple. Let's look at another example. Before we do, this actually should be in the next slide, but I'll go through it now. When we are using probability trees, remember your use of English. If you use the word and, it means multiplied by. If you use the word or, it means plus. Right? And means multiplied by, or means plus. We'll come back to it in a second though. Johnny has a 0.4 chance of scoring from a free kick and a 0.7 chance of scoring from a penalty. So if we look at the free kick, and we'll build up our tree. He can either score or miss, and the chance of him scoring from the free kick is 0.4. So if total probabilities have to add to 1, the probability of him missing is 0.6. Similarly for a penalty, he can either score or miss it. Probability of him scoring the penalty is 0.7. So probability of him missing is 1 minus 0.7, which is 0.3, and similarly below there. So that shows that he scores. The first lot is the scores the free kick, scores the penalty. Scores the free kick but misses the penalty. Misses the free kick but scores the penalty. And misses both of them. Okay. So how is this useful? How in the world could this possibly be useful? Well, let's have a look. We'll go back to our diagram where we're tossing the bass coin. We found out that it looked like that. So if we're going to find the probability of a combination of outcomes, we multiply the probabilities along the relevant branches. Think of it like this. What's the probability of 2 heads in a row? Well, to get 2 heads in a row, you need to throw a head and another head. And means multiply by. So you'd have 2/3 times 2/3. Highlight it using your tree, and you get 4/9. What's the probability of a head follows by a tails? Well, you need to throw a head and then a tails. Use the word and. We're going to multiply. So it's 2/3 multiplied by a third, which is 2/9. Similarly, a tails followed by a heads is a third times 2/3. It's 2/9. And the probability of 2 tails is a tails and a tails. It's a third times a third. It's 1/9. What's the probability of one head and one tail? Well, there are 2 different ways this can happen. You could throw a head and then a tail, or a tail and a head. That would satisfy what I've been asked. And if that's the case, you add the probabilities together. Think about what I said. I said I need a head and a tail, which is 2/3 times a third, or, which means plus, a tail and a head, which is a third times 2/3. Right? So it'll be 2/9 plus 2/9 is 4/9. And I'm going to point something out. If I had went back here and looked at these 4 probabilities, if I add those together, they add up to a probability of 1. 4/9 plus 2/9 plus 2/9 plus 1/9. That will give 9/9, which equals 1. Look at the second example, which was here. Probability scores both. Sorry. Is score free kick and score penalty, so 0.4 times 0.7 gives 0.28. Probability scores neither is he misses the free kick and misses the penalty. So it's 0.6 times 0.3 gives me 0.18. And the probability scores one of each. Well, there's 2 different ways he can do that. He can score the free kick and miss the penalty, so 0.4 multiplied by 0.3, or, which means plus, 0.6 times 0.7. It's 0.54 altogether. And again, if you add those up, 0.28, 0.54, 0.18, you get. Okay, so let's look at one question here, where we've given a partial tree diagram and we have to fill out the rest. Simon plays 1 game of tennis and 1 game of snooker, and the probability that Simon will win at snooker is a third, and the probability that Simon will win at tennis is 3/4. So we know total probabilities need to add up to 1. So when we complete this tree diagram, we know that if probably Simon wins is 3/4 at the game of tennis, probably doesn't win is whatever 3/4 adds up to 1 to give you. So 3/4 plus what gives me a quarter? Well, it's 1/4. Similarly, in the snooker, the probability he wins is a third, the probability he doesn't win is then 2/3, and similarly down below. So we're going to work out the probability that Simon wins both games. So he has to win tennis and win snooker, and being the operative word, so we'd have 3/4 times a third, which would be 3/12, which would simplify down to a quarter. Work out the probability he'll only win 1 game. Well, that can either happen by either winning tennis and losing snooker, or losing tennis and winning snooker. So it's 3/4 times 2/3, or, meaning plus a quarter times a third. And if I do all that together, I get 6/12 plus 1/12, and that gives me 7/12. And that's the end of the foundation video. That's as much as you need to know or do. Draw your tree diagram, and away you go. Remember the things we wanted to cover. If I go right the way back, I scroll back. Actually, could have just done that and went there. So silly. What do these mean? These means that all probabilities measure between 0 and 1. So probability has to lie between 0 and 1. And the sum of all probabilities has to equal 1. That's just what those 2 things mean. Probability is the number of favourable outcomes over total possible outcomes. Hope you got all that. If not, we're going to do a couple of experiments. It's going to be a bit of a fun class next week. So I'll make sure you're all there. There is homework down below that I want you all to do. Bring it with you or submit it or whatever, but please do it. Especially since it shouldn't take very long. And other than that, if you're to do the higher stuff, watch the next video. If not, I'll see you in class on Tuesday. Hurrah. Bye.